A 2,000-year-old machine pulled from a shipwreck could predict eclipses with bronze gears, and it was not even the only ancient invention that seems impossible. Today, we're counting down 10 ancient technologies that were centuries ahead of their time, ending with the one that forced historians to rewrite what ancient engineers were capable of. Imagine standing beside the Nile and watching water climb uphill. No electricity, no engine, just a wooden tube, a spiral blade, and a person turning a handle. That was the genius of the Archimedes screw. It solved one of the oldest problems in farming. How do you move water from a low place to a higher one without carrying it bucket by bucket? Inside the tube, the spiral trapped pockets of water. As the screw turned, each pocket moved upward, almost like an elevator for liquid. What makes it rank is not that it was complicated, it was the opposite. It was simple enough to build, tough enough to last, and useful enough that versions of it are still used for irrigation, drainage, and wastewater today. Ancient engineers did not just move water, they learned how to make geometry do the lifting. When Europeans first saw rubber balls bounce, they thought it was almost unnatural. But in ancient Mesoamerica, people had already mastered something that feels like early chemistry. They took latex from rubber trees and processed it into solid, springy objects. That may sound ordinary now. But rubber is not obvious. Raw latex can be sticky, unstable, and difficult to control. The achievement was learning how to turn tree sap into a material with bounce, grip, and durability. These rubber balls were not toys in the modern sense. They were used in ritual ball games that carried political, religious, and social meaning. The ranking comes from the material science. Long before modern polymers, these makers understood that nature could be transformed into something with engineered behavior. They did not have a lab coat, but they had a formula. Before paper became ordinary, writing could be heavy. Clay tablets were durable, but bulky. Silk was elegant, but expensive. Bamboo strips worked, but imagine carrying a library made of sticks. Then came paper. Traditionally associated with Kailan's improvements in China, paper turned information into something cheap, light, and portable. That sounds simple until you think about what it actually did. It made records easier to keep. It made letters easier to send. It made knowledge easier to copy. A civilization with paper can remember more, organize more, and teach more. Paper ranks here because it was not just an object. It was infrastructure for the mind. Every notebook, receipt, map, passport, sketch, and printed page belongs to the same ancient idea. Make thought thin enough to travel. For most of human history, direction came from the sky. Stars, sunrise, coastlines, winds. But clouds could hide the heavens. Storms could erase landmarks. Night could turn the sea into a black sheet. Then someone noticed that lodestone, a naturally magnetic mineral, had a strange habit. If it could turn freely, it aligned itself. The earliest compass traditions began in China, where magnetic direction was first tied to ritual and orientation before becoming a navigation tool. That is why it ranks so high. The compass took an invisible force of the planet and made it practical. It turned Earth itself into a guide. A sailor holding a compass was not just holding a tool. They were holding proof that nature had hidden instructions if you knew how to read them. A normal crossbow is powerful, but slow. You load it, you draw it, you aim it, you fire it, then you start again. The ancient Chinese repeating crossbow changed the rhythm. With a lever mechanism and a magazine of bolts, it could load and fire in one repeated motion. It was not the strongest weapon on the battlefield. That matters. Its genius was not raw force. Its genius was speed, simplicity, and mechanical repetition. In a tense defense, a person with little training could send bolt after bolt toward an attacker. The machine reduced several steps into one. That is why it feels ahead of its time. It took the idea of repeated fire, something we associate with far later weapons, and built it from wood, tension, leverage, and timing. It was ancient engineering thinking in sequences, but the next one changes everything because it did not attack an enemy. It tried to detect a disaster no one could see coming. The ground shakes, a city panics. But hundreds of miles away, nobody knows where the earthquake happened. In ancient China, the scholar and inventor Zhang Heng built a device meant to answer that question. The famous design is described as a bronze vessel with dragons around the outside. Each dragon held a ball. When the instrument detected a tremor, one ball would drop into the mouth of a toad below, indicating the direction of the earthquake. It was not a modern seismograph. It did not draw wave patterns or measure magnitude, but the idea was extraordinary. It turned a distant, invisible movement of the earth into a signal. That is why it ranks above weapons and materials. It shows a mind thinking beyond what the eye can see. The disaster happens somewhere else, yet a machine in the capital responds. That is not superstition. That is early detection. Modern concrete cracks. Salt water eats it. Time wears it down. So why are some Roman structures still standing after so many centuries? The answer is one of the most impressive material stories in history. Roman builders mixed lime, volcanic ash, and aggregates into a concrete that could become stronger in harsh conditions. Recent research suggests that tiny lime-rich pieces inside some Roman concrete helped cracks heal when water entered them. Think about that. A wall gets damaged. Water seeps in. Instead of only destroying the material, the water helps trigger minerals that fill the crack. This ranks so high because Roman concrete was not merely strong. In some cases, it behaved like a living repair system. The Romans did not invent concrete as we know it today. They did something stranger. They built with a material that could fight back against decay. A sword is only as good as the metal inside it. Ancient South Asian metalworkers developed a high-carbon crucible steel, often called woods. It was prized for its strength, edge quality, and beautiful patterns when forged into blades. The process was demanding. Iron, carbon-rich material, sealed containers, controlled heat, and careful cooling all mattered. Too little carbon and the metal was ordinary. Too much and it could become brittle. The achievement was control. Woods ranks because it shows ancient engineers working at the edge of what materials could do. They were not just hammering metal into shape. They were changing its internal structure. Later, this steel became linked to the fame of Damascus blades, which carried an almost legendary reputation. But the deeper story is better than legend. It is the story of craftspeople who learned that the secret of strength can be hidden inside the grain of a material. But the next one changes everything, because it looks like the beginning of the Industrial Revolution, sitting in the ancient world. Hero of Alexandria described a device called the Iolipoli. Picture a hollow metal sphere mounted so it can spin. Water heats below it. Steam travels into the sphere. Then the steam blasts out through bent tubes on the sides, forcing the ball to rotate. That is rotary motion powered by steam. It was not a factory engine. It did not pull trains or pump mines. It was likely treated as a demonstration, a marvel, maybe even a kind of temple spectacle. But that is exactly what makes it haunting. The principle was there. Heat becomes steam. Steam becomes motion. Motion becomes power. Hero's machine ranks near the top because it shows how close ancient mechanics came to a world that would not fully arrive for many centuries. The missing piece was not imagination. It was the whole system around the invention: fuel, metallurgy, economics, and demand. And now we reach the invention that almost does not feel real. Divers found fragments of it in an ancient shipwreck near the Greek island of Antikythera. At first, it looked like corroded bronze. Then researchers realized there were gears inside, not one gear, a complex arrangement of them. The Antikythera mechanism could model cycles of the sun and moon, track calendars, and predict eclipse possibilities. It was, in effect, an ancient astronomical calculator. That is why it ranks number 1. Not because gears existed. Gears were known, but this level of miniaturized mathematical mechanical design was shocking. For a long time, people assumed nothing this sophisticated appeared again until much later clockwork traditions. This was not a statue, a weapon, or a building. It was a machine for calculating the sky. Imagine holding a box, turning a handle, and watching the heavens become predictable. The Antikythera mechanism proves that ancient technology was not always crude, simple, or purely practical. Sometimes it was abstract. Sometimes it was scientific. Sometimes it was so advanced that when we finally found it, we had to catch up to the people who made it. So here is the question. Which ancient invention do you think came closest to changing the modern world early? And if you like this, the next video covers the top 10 lost technologies historians still can't fully explain.